start the... Okay, so welcome to everyone. This is another session of the Women in Network Science seminars. Today we have Xie He, which is a PhD candidate in applied mathematics at Dartmouth College. She holds a bachelor degree in mathematics of computation at UCLA. And she's interested in connecting network science and machine learning, especially through link prediction, which is on temporal networks, which is what I think she will talk about today. So the floor is yours. You have time 45 minutes, and then after there will be time for questions. Okay.
Gosh. Thank you so much, Alina. Thank you for the invitation. I'm really honored to kind of have the chance to speak today to you guys. And thank you all for coming by to listen to the talk. So today the talk is going to be link prediction, and my title is Learning to Predict, a Sequential Stacking Link Prediction Algorithm for Temporal Networks. And this is a joint work by me, Amir Giesman at Yale, Erin Lee, who's currently at Pakyong University in Korea, Aaron Closet, who's at CU Boulder, and my advisor, Peter Muka at Dartmouth. So a little bit more about me. Thank you, Alina, for introduction. I'm a fifth-year PhD student at Dartmouth College. I'm studying network science, and my advisor is Professor Peter Muka. There's a website about me that you can find all more information about me, the works that I've done, and the interests and hobbies that I do. And this is my cat. I had to introduce her. Her name is Sesame. She is very perfect. Yeah. So so let's talk about link prediction. We all know that networks is graphs. Networks is nodes and edges that are linked together, and links are playing a very important role in network science all the time, right? Like people care about nodes, people care about edges as well. And so in that case, we also know that networks are not static. So previously when we were before we were studying Zachary Karate Club, which is a static network. It does not change. It remains the same all the time. But we all know that with the information kind of flowing in right now, and with the technology growing especially, the data that we gather over the time becomes more important to us. And we all know people's relationship change over the time. And that's why we are focusing more on temporal link prediction instead of static link prediction right now. So why do we need link prediction on temporal networks? So real-world networks are, like I said, completely often changed over time and temporally changing all the time. So for a better recommendation system, we need to consider the temporal features of the networks. For example, the best sort of like example that I always like to use is the Facebook network. Like people tend to friend with each other or unfriend someone that they don't no longer be friend with, and that's like basically a disappearing of a link and another connection of a link. Another example, perfect example for the application side of the link prediction will be like a recommendation system. So that will be like on a bipartite temporal network, and that will be like recommending a user a product from a website, right? Like the user behavior change all the time, and they keep some of their habit. For example, if I own a cat, I might buy cat dry food every month. And so the prediction will just recommend that dry food to me every month. But it can also change my habit. For example, I might move out and I might adopt another dog. So will the recommendation system learn to sort of like predict what's my next move will be an important feature in designing these type of architecture. And another thing that will be like a good example of transactions on temporal networks will be like a financial transaction network. So for example, like if two businesses are cooperating with each other a lot, then naturally I'm going to recommend a transaction. I'm going to predict a transaction is going to happen at the same time next month between A and B, the companies A and B, at around same time. However, for example, like if C also comes into play at some point, will C effectively have another financial transaction with either A or B, because C is somehow in between the area, or maybe like company A want to develop like or grow their business based on some other aspects, and that will all become like a very important point in predicting the future, as I like to say. So it will be like a prediction on temporal networks. So we want to sort of like generalize the stacking methods on the temporal networks. So if you recall previously, I was showing this figure on the right-hand side. As you can see, these are the stacking methods for a static network. So basically for a static network, what we try to do, what Giesman et al., which is my collaboration and second author on the paper as well, is that they try to extract topological features from a static network and use that as the feature vector to do the prediction for static network. And what we want to do is that we want to sort of extend this idea to temporal network and see if that's going to help us or not. So before we show what we have designed for our algorithm, we want to sort of talk about what people usually do. So very sort of like usual or common standard state-of-the-art method for temporal network link prediction is that they will try to use temporal network properties. And by properties, what I really mean is temporal topological features. For example, we all know common neighbor plays a very important role in static network link prediction, and that information could also be extracted out and used for temporal network link prediction or temporal link prediction. And we also seen people using a lot of stochastic block model and matrix factorization. This is sort of like a very standard, for example, the ALS algorithm is very often used in recommendation system and are highly adoptive in the industrialized sort of a recommendation system criteria. This is heavily based on treating the whole network as a tensor instead of focusing on localized structure, as you can imagine how like the matrix factorization are used. And the other method, of course, it's machine learning based. So these methods, sometimes they are using traditional machine learning, sometimes they're using a more profound neural network method or embedding method. And these methods are highly accurate, I can say, but they are also really hard to interpret. So they are very based on data, so like sort of data-driven method. So the more data they can gather, the more GPU they collect. Of course, basically, the more money you have, the better prediction you will be able to do for larger networks. But the interpretability and explainability of the features is always lacking in that type of method. And as we often like to see in the network science community, the median sized data will always be the most interesting sized data to look at. And so these are the sort of three methods that we're trying to kind of like look at right now for the temporal link prediction. And we want to sort of combine them together, sort of, so to speak, because they all have their sort of benefits and they all have their weakness. But what if we can kind of like come up with something that combine them together to make it even better? So that's when we were thinking back about that static network topological feature paper, right? So we want to find out a way if we can use the static network topology, because if we're going to use the temporal topological features, the calculation itself is going to take a long time, as you will see in the later on slides. But the static network properties are really well defined, right? They're easy to calculate, like to name a few: degree, betweenness centrality, page rank centrality, closeness centrality, etc. Right? Like, so they're all really well defined. They're easy to calculate. They're available package on Python, MATLAB, or R, and they have like a very good explainability as features, and they've already been seen to shown to work on static network pretty well. So that's something that we find really helpful, and that's something that we want to adopt into play for the temporal topological feature, for the temporal networks as well. Because temporal networks, if you're calculating temporal topological features, think about, for example, betweenness centrality, right? You have to calculate first of all the shortest path for that network and for each of the node if you're actually going to model each of the edges individually. And that's very, very expensive. In fact, it's if I recall correctly, I think it's big O of n squared times m, where m is the number of layers in that temporal network, and n squared is of course the number of nodes in that network. So you can imagine that for a large network, that number goes exponentially, polynomially really fast, right? So, and we don't want to do that. So that's why we want to sort of utilize this static network, really good and really nice features to do what's good for us. And so before I even go down into describe the algorithm, sorry, I promise this sort of preliminary is going to be over and we're going to look at the algorithm soon. But before I even do that, right, like we can imagine that for static network, this is often like a very this is actually a question that I get asked very often. People ask me like, I can imagine what happens for like a static network. Link prediction might just mean that the partial of the network is missing and we're trying to kind of recover the data per se, right? But what is the usage if we're doing the temporal link prediction? Wouldn't the network already information be complete for the past layers, and what are you actually trying to predict here? And this is sort of like a place where I try to explain this. So for static network prediction, you can imagine if you're looking at, I'm not sure if you can see my mouse right now. Yeah, I think it's right here. So if you're looking at this plot, right, like the sort of dashed edges are the one that you're seeing on this plot, and the sort of like solid edge are the edges that you're seeing, and the dashed edges are the edges that you're trying to predict for a static network. But for temporal networks, it's not the case. So for a temporal network, what usually happens is that, for example, in T0, the network look like this, and for T1, it changed a little bit. So the edges from pointing from C to B is still kept, but the other two edges changes. And what happens for temporal link prediction is that we adopt the setting for the static link prediction, but we also change it a little bit. There are two different conditions. Namely, I can partially observe the target layer that I want to predict, for example, T2 here. I can actually try to predict what's missing right here, or on the other hand, I can try to predict this layer entirely. So I can assume that I know nothing at all about T2. So to give you an example about the differences between the partially observed target layer and the completely unobserved target layer, think about that we are almost at the end of September right now, right? Like, so let's assume that we have some information from August about maybe like a social network, and we also have some information about from July about that social network, and we're in the middle of September right now. We are actually September the 25th, and we're trying to predict what will happen in the next 5 days. So how will this social network change? And that corresponds to this partially observed target layer. And on the other hand, let's just say that we're on September 30th, and we know everything about July, August, and September, and we know nothing about October whatsoever at all. So our goal now will just going to be predict what will the network look like in October, and that is going to be our completely unobserved target layer case. So that's the two essential difference between these two settings, and the difference between the temporal link prediction and static link prediction. So after clarifying this, I think I want to also sort of like talk a little bit about the basic setup for this algorithm. So for this algorithm specifically, I also asked whether it is a continuous time window or it's discrete. But for this one, it's discrete. So like each layer is its own temporal snapshot. And so, for example, like if I have a network that's daily information, then my layer will be each day. If my network is not, like I don't have enough information from every day, then maybe my network for each of my network layer, it will be like a week of information or a month of information. It will just be its own temporal snapshot of information. And the diet for this paper is sampled uniform randomly. And this is actually pretty important. I'm going to mention this at the very end, but just to keep you in mind that the training data and the testing data are sampled uniform randomly from the network. And the performance measure are provided via AUC score. It's pretty standard for link prediction algorithm to be measured this way. And so, yeah, so let's dive down to the model. Now comes the interesting part. I know this plot is a lot, and I will try my best to explain this. Feel free to ask any questions or comments if you have any. So as you can see, so the first thing you see in this plot is that it have different temporal layers. And yes, indeed. So for this plot, it is a toy model. It has 6 layers. And the last layer, which is colored in red, is our target layer. So this is the target layer t equals to 5 that we're trying to predict. And all the green layers is our training layers, or the past layers that we already have information about. So you might ask me, okay, so why is there a layer in white? And that's where I come to explain the search variable u. So search variable u is settled in the sense that it is a parameter that you can adjust in the algorithm. And you can set it to be, for example, in this toy model, I set it to be 4 because maybe fashion is a cycle and we do enjoy the clothing in 90s, but predicting future in machine learning is not. And we cannot sort of use 100 years ago's data to predict tomorrow. So what happened is that there are some outdated information. There might be some outdated information in your data set. You might have too much information needed, in fact, to do the prediction for your future prediction in t equals to 5. And this is where the search variable u equals comes into play. U is basically controls how many consecutive layers, previous layer you take for your data set to be your training data set to do the prediction on the last target layer. And I also have like another variable q. And let me explain a little bit about like what q does. So this plot you are looking right now is actually explaining the model about the completely unobserved model, and it's not representing the partially observed model. So in that sense, t equals to 5 is completely unseen. And anybody in the room who does a little bit of machine learning knows that I need training data and testing data. I need feature vectors for both training data and testing data in order for the algorithm to even work, right? If I completely unobserve t equals to 5, how can I even generate the feature vectors for t equals to 5? And that's sort of like the amazing part about this algorithm is that q equals to 2 means the number of consecutive previous temporal layers considered in this sequential stacking. I actually made a typo there. There's a missing g, but yeah, that's so basically you're taking the feature vector produced from t equals to 3 and t equals to 4 as your training, as your feature vector, and you're using the label from t equals to 5. So for example, you're confused here a little bit, but like basically what happens is that think about 1, 2, 3 as a combo. 2, 3, 4 is a combo, and 3, 4, 5 also as a combo. And for 1, 2, 3, I'm generating the information using the static topological features from t equals to 1 and t equals to 2. I stack them together, but I extract the labels from t equals to 3 and use that as my training data. And the same thing for 2, 3, 4. And for 3, 4, 5, it's my testing data. It's the thing that I'm trying to predict. So what happened is that I extract the information from C3 and 4, but I'm using the label from 5. So in that sense, I never ever touch the information on t equals to 5. And that's where I'm trying to predict whether there is a link or not. I'm only using the t equals to 5's information from my testing labels. And so to avoid any sort of like accidental usage of the testing data in the training phase, right? So this is basically how the model come to work. This is not representative again about the partially observed case, because for the partially observed case, basically, I'm also going to take a little bit about the information from t equals to 3 to add on these feature vectors. But you can imagine like this plot is already complicated enough, and if I'm going to do that for the partially observed case, it's just going to basically be too much for me to do. So, and that's why like if anybody has like a good idea about how to draw out the case for the partially observed case, I would highly appreciate if you talk to me after the talk. Now to experiments and results. So let me give you like a little bit overview about the data sets. So for this experiment and paper, we gathered 19 different real-world data sets from different domains. As you can imagine, the previous example that I give you include college message, which is just like a social network. And we also have Bitcoin Alpha Trust, which is a network that I took from the Icon website. And it's like a financial transaction network. We also have like an animal social network, which is just ant colony network, and transaction like transportation networks like London biking network. So it kind of includes a wide variety of different types of networks from different domains and areas. And so let me go to the next slide. So this is where we talked about the synthetic data sets. So in order, like, of course, this algorithm is very complicated. And so like other than a real world data set, we also want to test on some sort of data set that we already know the features about. And that will help us understand what's going on in this algorithm better. And so let me explain a little bit about the two types of synthetic data set that we use in this paper. So the first one that I'm going to explain is the community TSBM model. The community label TSBM model, so TSBM stands for temporal stochastic block model. And so this model is focused on keeping the community label. And it's actually better phrased to as community correlation model. So basically what that means is that, so let me first explain the three parameters here. P in this model represent the node label correlation between the previous time slot and next time slot. And what the node label here essentially means is that how likely is a node going to stay inside the same community across time? And what mu represents is the fraction of random edges added onto the SBM model. And K represent the number of different communities inside of that SBM model. So basically, after explaining these parameters, I hope it's pretty intuitive as to what community label means. It basically means how likely a node is going to stay inside the same community over time. And so the other model that we use for this synthetic data set is the edge correlated TSBM model. So again, here P, actually let us skip P for now and go to mu and K first. So mu and K still represent the exact same thing. So mu is the fraction of random edges added on to kind of mixture this model, SBM model, and K still represent the number of communities inside of the model. But P now means how likely is an edge going to remain an edge in the next time step, and how likely is a non-edge going to remain as a non-edge in the next time step. So to make it easier, for example, like there is an edge between node A and B in T0, then if my P equals to 0.8, that means that edge is going to still exist, for example, here between A and B in T1, and vice versa, the same thing. Right, so that's basically how this two model works. And let's look at some of the this is some of the interesting results that we have gathered. So this one is the temporal common neighbor. And specifically for this plot, we are only looking at the temporal common neighbor. So as I have previously discussed, it's really time consuming to calculate these temporal topological features. And temporal common neighbor is actually the easiest one to calculate. And that's why we're looking at this first. As you can see, if we are looking at the sequential features instead of the temporal features, sequential feature in general does a little bit better than the temporal features on some part of the real-world networks, and it's on par with the temporal features for other part of the real-world networks. And for the community labeled TSBM, it's almost always that the sequential features are doing better than the temporal features. And for the edge correlated one, they're about the same. And this is very explainable for the two synthetic networks, because intuitively speaking, right, like for the edge correlated case, you know that it's all going to be dependent on the edge and dependent on the previous information. And so in that case, if I'm looking at the temporal common neighbor, it's going to be consistent across this temporal layers, and that's why they are on par with each other. But however, for the community labeled TSBM cases, the temporal feature is going to change over time, and so is the neighbor. So the neighbor is the community identity might not be that different, but the neighbors is definitely going to be different every time. And so that's why the sequential features is doing better than the temporal features. And for the real world networks, this is also very interesting to look at, because you can see that the two synthetic networks is actually capturing the different features of the real world network, in that like some part of the real world network may behave more like community label TSBM, and other real world networks might actually have like a characteristic more closely related to edge correlated TSBM. And that's something that's really interesting to look at. And I'm also showing, so like we all know common neighbor is actually pretty cheap to calculate, and it's also a very simple feature. So we also want to look at something else. So here is the something else. Here we include 4 different temporal topological features, including degree centrality, closeness centrality, betweenness centrality, and network latency. As you can see, for all these centrality measures, on the left-hand side, we have not all of them, 3 of them. On the left-hand side, we have the time complexity of the comparison. So it takes much longer to calculate the betweenness centrality score, the temporal betweenness centrality score for temporal networks than calculate the sequential betweenness centrality score for a temporal network. So for here, what you're looking at is basically the time differences. As you can see, only in the case where the degree centrality that the sequential stacking is taking longer than the temporal centrality, and that makes a lot of sense, because the temporal degree centrality would just be an aggregation of the degrees over time, right? So it will only calculate once, but the sequential stacking has to calculate several times about the degrees in different layers. And in all other cases, for the closeness centrality, betweenness centrality, and network latency, temporal topological feature is actually taking a long time to compute, and they are not doing that much better than the, actually they're doing worse than the sequential features, as you can see on the right-hand side. So for the y-axis, it's the AUC score from the temporal features, and on the x-axis side, it's the AUC score from the sequential features. And you can see that the sequential feature is almost always doing better than the temporal features by themselves. So that gives us to the real world networks and insights. So this is the place where I want to sort of like go through carefully about what happens, is that because there are many information here. So as you can see on the top labels here, top sequential feature and ensemble sequential stacking are 2 different things, and they're colored differently. They mean entirely differently. So top sequential stacking is what I have just described before. It's using only the topological features, the static topological features stacked together as feature vector to do the prediction. But ensemble sequential stacking is completely different. It is actually taking all these information, so including the time series, the top stacking, the tensor SVM, and ELSTMD, all of them included together to do the prediction. And that's the sort of like the whole point of this paper, is to tell you that if one method is not going to work for all of them, and as you can observe clearly that none of the sort of like the single method by itself is doing the best, right? Like none of it's doing the best, but if you can combine it together, it might actually do better. And as you can see, for the 19 real world network cases, only in 2 of these that ensemble sequential stacking is not doing the best. And in all other cases, it is achieving almost close to the best AUC score, albeit for some of the network, it might be lower, some of the network, it might be higher. But that's what my point is. Basically, it's trying to do its best job by combining these predictors together. And the real world networks are so complicated that none of the single predictors can do a good job on all of them. So in this case, especially, I want to point out that for the part A right here, what you're looking at is for the partially observed case. And for part B, it's the completely unobserved case. And that's why you're observing that for the partially observed case, on general, the prediction algorithm is doing better than the completely unobserved case. I mean, for sure, because it's different, right? Like it's the partially observed case have more information to start with than the completely unobserved case. And so I also want to talk a little bit about the stacking feature importance. This is the other part where I think it's really important and interesting to look at, especially if you combine this plot with the previous plot that I have just shown before for the real-world network. So for all of the real-world network, actually, they are doing very differently. And by very differently, I mean the most important features captured by the algorithm is so different. Actually, all of them are different. Even though for calling networks, for some of the like more similar networks, they may look similar to each other, like some of the important features, for example, the DLRA approximation score might always be there for the colony networks. It's almost different for each single one of them. And that's my sort of next important point, is that when you're trying to do like a prediction algorithm for any kind of real world network, you cannot always assume that even though ensemble learning is doing good, you cannot still assume that it's going to solve every problem of yours, because each network is so unique and so different that you have to pay very special single attention to each and every one of them. And so this is sort of like a plot by showing the feature variance of among all of them. However, my second point on this, using this plot, is that even though some of the sort of like the networks are different, and so different that each individual features are different, they still have something in common, right? Like as you can see, the outer network, again, DLRA is already there. Network degree is also kind of pretty useful in doing the prediction for these kind of network. And for the other networks, like I will say like the PRP, which is the page rank, will be very important for these type of networks. However, for all these different types of network, we can also observe that the ensemble learning is doing good on almost every one of them. And that's sort of my whole point, is that for different type of networks, SBM and ELSTMD, sorry, I didn't explain this earlier. Let me do this. Sorry. This thing is like I believe everyone here probably experienced this at some point in their life, is that you've seen this so much, you assume people know this, but actually people don't. So sorry about it. Let me explain this better. Is that ELSTMD represents a LSTM method, which is a neural network method doing the embedding and doing the prediction. And time series just means in using the ARIMA to capture the topological features and doing the ARIMA as features to do the prediction, while tensorial SBM is basically using the original tensorial SBM, which is a stochastic block model method to do the prediction. And top sequential stacking, of course, is just using topological features, static topological features stacked together to do the prediction. And ensemble sequential is combining all of them to do the prediction. And as you can see, some of the ELSTMD is doing really good, and including tensorial SBM, but they're not going to work for all of the networks, while the ensemble learning is going to combine their strengths together to do the prediction. And one more thing that I want to explain, again, sorry for the oversight, is that you can see that the tensorial SBM is not appearing in this plot, even though it's appearing on the left-hand side. And that's sort of expandable, is because not every one of the methods works for a completely unobserved case. So specifically for SBM method, from what I read so far, you might have different opinion on me. Please let me know if you have find other like papers related to this topic that I have not seen before. Is that like, I think all of the stochastic block model requires you to have some prior knowledge on the target layer in order to do the prediction. And that's one of their weakness, is that they can never do the prediction without any prior information about the target, about the future per se. So this is sort of like to do a further explanation on how things work for real-world networks. And I'm going to move on to the synthetic networks data sets. So again, I apologize. I know this is a lot. I will try to do my best. Again, these are the 5 methods that I have just worked you through with the real-world networks. We're using the exact same colors for all of them. And this is the results for the partially observed case. On the left-hand side, you have the community label TSBM, and on the right-hand side, you have the edge correlated TSBM. And so you can see that for the partially observed case, the ensemble sequential stacking and top sequential stacking are almost, and together actually, time series is also doing really good for this kind of two types of synthetic data sets. These three methods is actually proved to be working pretty well. And I have like my theory on this, but I think also because that the ELSTMD is not doing so good because the network is relatively small. These synthetic networks have around 200 nodes. And I'm pretty sure that if we increase sort of like the data size amount, the ELSTMD might actually do better because it is shown to do pretty not that bad on all of the real world networks. And so this is sort of like just to say that the dashed line right here is the Oracle level performance. So we actually did an analysis. We did some math. Albeit you might see this as a machine learning paper. We did some of the math. We calculated the optimal upper bound of the synthetic network's AUC score. And by upper bound, what I mean is basically if an oracle that knows everything about the network whatsoever at all, it knows everything, it knows the P, it knows the mu, and it knows the K, what will be the performance of this oracle method? And that will be the dashed line. As you can see, so some of the green ones are really close to the dashed line for the edge correlated cases. And in general, the edge correlated case is easier to predict per se than the partial, than the community label TSVM. And this also makes sense because in this case, if I set P equals to 0.6, it means very different thing than in this case, if I set P equal to 0.75. And I intentionally change it to be a lower level of P because if I change it to be 0.9, that just basically means copy and paste my network from T equals to 0 to T equals to 1, right? So that's sort of like an interesting to see for this two networks. And I'm also showing you the results from the completely unobserved setting as well. So for the completely unobserved setting, you can see that in general, even though the edge correlated case is doing almost the same thing, the community label cases, actually, all of the algorithm, including top sequential stacking and time series and ensemble learning, are doing a bit worse than the partially observed case. And that kind of makes sense. That really makes sense a lot because essentially, think about it. I have more information about my target layer in my partially observed case. I have no information whatsoever at all about it in my completely unobserved case. Naturally, I'm going to do worse in the completely unobserved case. Albeit, I want to point out that it's still doing relatively good for some of the higher number of communities. So here again, the number of nodes in all these synthetic networks is capped at 200. And so I kind of want to sort of wrap up my conclusions. So for this paper, basically we designed a stacking method to capture the temporal flow for link prediction on temporal networks that works for both temporal link prediction settings. We do a comparison between the temporal stacking features and the stacking features and the temporal features to show that the stacking feature are a very good surrogate, if not better than the temporal features. And we also show the possibility of learning to improve the performance of the stacking method through incorporating other advanced machine learning or SBM methods and achieve a good result on different types of real-world networks. So my sort of future direction for you guys is that if you listen carefully to my previous talk, I mentioned a very kind of specific point is that we are using uniform random sampling for this method. However, if we not use uniform random sampling and we actually use a bias sampling method, then the result is going to be pretty different. And this is sort of the thing that I'm currently working on is that I have taken around 250 real-world networks and 21 different sampling methods and 6 different link prediction algorithms to try out how like the link prediction algorithm and sampling method and different kinds of real-world networks is going to affect each other. I do have a plot for the results for that paper, but it's too big. So you're welcome to talk to me after the talk if you want to see the plot and we can discuss more on this. So this paper is in preparation to submission right now. And the temporal link prediction that I talk about today is on reviewer stacks for 9 months now. So we will hope that it will answer sometime soon. So thank you so much for listening to my talk today. I'm really honored that I have the chance to talk about it. And I'm happy to take any question.
Thanks a lot for this talk. It was
Thank you, Alina.
very interesting. Are there any questions? Okay, I see a question in the chat. I can read it. What is the relation between Q and U? Say if U is equal to 2, how would you break down the stacking?
Sure. Let me go back to where I'm showing U and Q. So essentially, there is so what if U equals to 2, right? Like, so essentially what we want to do is that almost always you want to set U to be larger than Q, because if in this case U equals to 2, then essentially what I'm going to do is that I'm going to take 3, 4, 5 as my training and testing data set together, and that's not going to work, right? So in this case, U has to be larger than Q. So if U equals to 3, for example, like in this case, then it will be 2, 3, 4, and 3, 4, 5. And that's going to work, but not if U is equals to Q. Thank you. That's a very good question, actually.
Yeah, I hope
And
Agathe, if you have other questions about it. And then there is a question from Yazaman.
Yeah, that's my name. I'm also a PhD student working in the same topic, and I would like to ask you to go to the part that you just explored a P in your model. You wanted to see how is it working with different P and how what are the AUC scores. Is it possible?
Sure, of course. So right here.
Yeah, definitely. Yeah. I would like to say that what is the number of nodes you wanted to look for this? Because, I'm just working on the same topic, and I understood that when you just choose your number of nodes around 100 or 200 or just a little bit less, it's not going to be predicted so well. But when you just increase your number of nodes to 1,000 or probably 2,000 or more, it's going to be much better. We had this problem before with the modularity maximization, with the community detection, with any kind of this topic, link prediction is also related topics to this one. So I would like to say, what is the number of nodes going on with this? Could you please explain a little bit?
Yes, sure, of course. So in this experiment, I specifically choose the number of nodes to be 200, mainly because that I want to have like a faster sort of experiment phase, if that makes sense. Because I have, as you can see, many different experiments that I need to run, and for specifically, I choose it to be 200 because the Tensor SVM have like a nested, like I'm using their own code. They have a nested for loop for like 5 for loop, and it's taking forever if I'm increasing my number of nodes to be like 1,000-ish. And this is specifically used because of the comparison metric phase, like comparison metric and for other methods. But I can totally relate to your topic and your question about like if I increase the number of nodes to 1,000, how is it going to behave? And I can actually answer this question by looking back at my real-world networks. So if you recall my introduction on the real-world networks, as you can see, some of these real-world networks are really large. And for these really large networks, the performance of the algorithm is actually pretty good as well. And so my imagination is that even if I'm going to increase the number of nodes in the synthetic networks, for the algorithms, it's going to be on par with about what it's doing for the number of nodes equals to 200, albeit it's going to be a lot slower. And that's the reason why I'm choosing the number of nodes to be 200. Does that answer your question?
Yep, a little bit, but I would like to ask further question, but I would like to stop here and let other audience ask questions. So if you had time, I would like to discuss a little bit more.
Of course.
So I don't see questions in the chat, so you can go on asking.
Yeah, it's all right. So there was also something for your data sets that you use. I saw that there was some problems with the Bitcoin, and the AUC score was around 0.5. So, just AUC score about around 0.5 means that we did nothing actually based on whatever you have done. So could you please explain me what features or explanations do you have for this, especially for this one, or the one that, that I see that there are very low scores on this? Is it because of the structure of the network, or probably because of the things that happened, on the topological aspects?
So that's a very good question. So my answer to that question is I don't know. Like, I hope that's a satisfying answer. Sorry about that. So for all these networks, again, they're taken from different domains. And so my sort of whole point of using this presentation here is trying to say that for different domains, we really need, as applied mathematician, we really need to talk to the domain expert in order to understand what's going on in these networks. And so far, what I can say is that I have been working with sociologists a lot. So I do know that for social networks, any kind of link prediction, that's as long as you have like included some part of the clustering coefficient in your algorithm, it's going to be good. Because social networks, they are really easy to predict and no question asked. But for financial transaction networks and biology networks, they're so different for each and every one of them. You just have to kind of look more into details about the network itself in order to figure out why your prediction is working or not working, or like why is it happening right there. So my answer to like why the Bitcoin network is like about 0.5 is that I don't actually know the reason behind it, because the main point of the paper is the algorithm developing, and so I did not pay very detailed attention to all of the individual networks.
Okay, probably further discussion can be made and we can just do it by email. Thank you.
No problem.
There is another question in the chat. So you have lower or upper caps on the U and Q. Do you have any other assumption for the algorithm or the data set, like being a time series?
For the algorithm, do you have any other? Oh, yeah, thank you for the question. Like, I don't really. So far, let me go back to here. Right, so I do have like a lower and upper cap for like U and Q. It's like not strictly speaking a lower cap or like an upper cap, but like U has to be lower than Q in order for the algorithm to work, right? Like, so another, like, there's not really any other assumptions other than that. Like, there's not really like any time series assumptions on the data set or the model itself. Like, the time series that you have been looking at in this plot right here is simply I'm using a ARIMA method to gather all of the topological features and use that ARIMA created average out temporal like sort of time series feature as my feature vector, if that makes sense. So there's not really any time series assumption on that. But like, I do appreciate this question because it provides a very useful insight. And that's the exact reason why we're talking about the synthetic networks right here, is because like we do really want to know how the time, like the temporal correlation is going to come into play if we're going to do the prediction. Thank you for the question.
Do we have any other questions?
So will I bother you if I ask more questions regarding this?
No, of course, please go ahead.
Yeah, could you please go on to the next slide?
Sure. Which one? This one?
Yeah, the one for the completely observed setting. I would like to say that I understand that when the target is not fully observed, I understand what does it mean. But when it's completely unobserved, I cannot say that what these numbers can show, because I see many low scores in AUC and your network is very well defined, and I don't understand why these scores are so low. Could you please give me some insight about what is going on, especially with ELS? And I mean, I don't get why this score is around 0.6, 0.5 in most of the cases. And I didn't also understand your discussion based on this ELSTM.
So the ELSTMD, so it's not my method. First of all, it's like one of the neural network methods. So what the neural network method they are designed for is basically it's designed for like you should have some of the information about the target layer, but it can also be used because they are pretty adaptive. So for a completely unobserved setting, and then like so I would so I would say that some of the real world networks, they are sorry, not the real world networks, the synthetic networks, the synthetic networks, they themselves, like if you don't really have any information about the last layer and you simply know how the previous layers goes, there might be some kind of noise. So like even though I'm setting like p equal to 0.6, it's not necessarily all the case that it's going to be like exactly 60% of the edges were kept as edges and non-edge kept as non-edge. In fact, mu equals to 0.1, 0.2, and 0.3 really is like pretty important right here, is that like a lot of the random edges will come into play, and also the number of community matters as well. So I don't really have any good explanation for you as to why ELSTMD is not doing really good for like a complete I guess not no explanation, but my explanation for like why ELSTMD is not doing so good is that it's not like designed specifically to capturing like a completely unobserved target layer, if that makes sense to you. Because like for a completely unobserved target layer setting, it's basically assuming that I know the labels from that layer, because I'm using like I have to know the labels from that layer to use it as a test set, right? So like if I don't have that information, then nothing is going to work. But like I'm only going to use the labels from that layer as my test set, and that's all the information I have basically. And as you can see, some of the ensemble learning is actually going to capture some of the features from the previous layers pretty good, but especially for the community label cases, it's not going to capture all of the information naturally, because the community label information is only going to provide you with a which community this node is more likely going to be in, and the topological features is going to capture part of that, which is why the ensemble sequential stacking is doing better than ELSTMD, because ELSTMD essentially is not using the topological feature. It's basically like a transformers, right? Like if you imagine, it's basically embedding the network. And so when you do that many layers of embedding, you basically lose any explainability. But if you're trying to capture at least some part of the topological features from that network, you at least have some understanding about which community that node is going to remain in. And that's why ELSTMD is not doing as good as the other three methods. In fact, it's not only like ensemble doing good, right? Like you can see time series is also not doing bad, because time series is also capturing some of that community like information from the previous time slots.
Okay, perfect. I will look further on these things. Thank you.
Thank you.
I also had a question, but I saw it in your future directions, because so you use random sampling. And do you think that changing the type of sampling will significantly change the situation?
Actually, I do already have some results on that. So like changing the sampling is definitely going to affect some part of like the results. For example, like there are two very popular methods, sampling methods that people like to use like nowadays, which includes DFS and BFS. And my experiments on over 200 neural networks have shown that actually if you use those two sampling methods to sample the edges as your training data set, your results is going to be worse than if you're using any other methods. So my recommendation is that if you're doing link prediction, avoid using DFS and BFS. But that sort of manuscript is still in preparation, and I hope that the preprint is going to be on archive soon. And before that, like if you have any question, you're welcome to talk to me about it.
Okay, thanks. Are there any other questions? I don't see other questions. So let's thank today's speakers for the presentation, and see you all next week for the next seminars.
Thank you so much for coming by, everybody. Thank you. I'll see you later.